So hi everyone, I'm Adam. Sorry for my voice, I just got a call yesterday unfortunately, but hopefully I'll make it through. So yeah, I wrote a lot of code in PyTorch. I'm kind of sometimes working with Facebook a lot, and I'm also like a student at the University of Warsaw in Poland. So the session I'll be doing will be pretty much a live coding session with a lot of hands-on experience, and like you feel free to like interrupt, raise your hand, ask questions if anything will be unclear. I'll just stop and start explaining there. Also just to get some feel, like how many of you have already used PyTorch at some point? Okay, so we have some beginners, all right. Okay, so I'll start with some things that Sumit already said, but I'll be like typing them and explaining them more in depth. So the most, of course, important thing is to import the package. You just type import torch and you have it. We have, unlike NumPy has like a single ND array type that then has like an internal field that specifies what kind of what's the data type of the array. In Torch, it's slightly different. We actually have like a separate type per data type. So like we have a float tensor, we have double tensor, we have half tensor, which is like FP16 half floating point format. We have byte tensor for bytes, char tensor for signed bytes, short, long, int tensors, basically. And also, if you want to use Cuda, in Cuda package, it also has like float tensors and all this. So this is exactly the same. So one important pitfall for beginners is if you create a tensor, it actually comes as uninitialized data. So you can pretty much see anything in here, and it will probably change between runs. So this is mostly for efficiency reasons. We'll probably be changing this to be zero initialized always at some point. But yeah, you often just want to like pre-allocate some storage and then like fill it in with results of some other things. So sometimes it's basically better to not pay for the cost of zero filling the memory. Yeah, but for demo purposes, there are a few handy functions. So there is rand, which returns uniformly sampled numbers from 0-1 interval, and rundan, which returns numbers sampled from normal distribution. Also, the convention is slightly different in NumPy. So in NumPy, you would probably specify the size, the shape of the thing in parentheses, and here it's just like a variable list of arguments.
Sorry, can you make it larger?
Oh yeah, sure. That's not an English keyboard, so this makes it slightly harder for me. Yeah, but the signs are different, so. Yeah, that should be the plus, but it doesn't work.
Oh, because control, okay. Not command.
Oh, should I use control?
Control, yeah.
Oh, it's Ubuntu. Okay, right. Yeah. All right. So that's for creating tensors. We do adopt some of the NumPy ways of accessing this. So we do support indexing by shape. A more sort of torchy way is to call size. We inherited a lot of API from Lua Torch. So if some of you use that, you might feel more familiar. Then for most tensor operations, there are a few ways to run them. So the most basic one is just calling methods in tensors. So if this is x, I can just do x add 1, and this will basically add 1. Another way is we have a sort of purely functional interface, so you can also do this sort of like NumPy does. And then there is also another important thing. We do support a lot of in-place operations. In NumPy, you usually use the functional interface with an out argument. in Torch, we just add a suffix of an underscore, which means that this operation will be mutating on the tensor. So now if you run this, it will actually change the x. All right. What else? So if you want to, I have to get used to different shortcuts. I want a new tab, not trash. All right. So most of the operations are in the docs, so that's probably a good reference. The names of the ops are the same both for the functional interface and for the tensor interface. So docs for the tensor interface are here, functional is here. So you can just like scroll around and look for some things you need. What else do we have? So now that we have X, there is of course this NumPy bridge. So the NumPy bridge is basically zero cost because they share the same memory. So we're basically only creating a sort of struct that describes the NumPy array. But it's like only like manipulating a few bytes every time you do this. So that's why it's extremely cheap, and that's also why changes in the tensor are also reflected in the NumPy array. It's not so cheap for Cuda tensors, obviously, because NumPy doesn't support Cuda, so we actually have to sync up with the GPU and copy the data to a new CPU tensor. So that's like one important disclaimer. All right, so I guess it's time for us to move to Cuda. So if you want to send a tensor to GPU, you just use the Cuda method. It accepts an argument, which is a device ID. This machine unfortunately has only one GPU, so I will be sort of only explaining how to ship them between multiple GPUs. In theory, I can't actually do that. So GPUs are always numbered from 0. So if you don't specify anything, it actually defaults to the current device. If you want to change the device in which the code executes, we have a context manager for this. So you do with torch Cuda device, and you say 2, and that's the third GPU. And now you can start typing code in here. So if you do this, this will basically create a 2-element tensor on GPU 2. Or, oh my god. Or if you do x.cuda right now, this implicitly will send it to device 2. You can always specify the device explicitly as well, and this will actually send it to device 1. So one important thing to remember also for beginners is that when you call x.cuda, first, Cuda call takes a while because it has to initialize the runtime. So here you can see that it actually returned a torch Cuda tensor, and it's in GPU 0. So one important thing is this call doesn't modify the original tensor in any way. If you call x right now, it just returns a CPU tensor. So if you actually want to like replace x with something that will be on the GPU, you have to do that. And from now on, x will be a Cuda tensor. Cuda tensors have exactly the same API as CPU tensors. We support, I think, all operations except for maybe 2 that are, some of them are even underway, so you just can seamlessly transition to this with just adding a few Cuda calls. So for about serialization, because that's an important part for machine learning models. So you can use Pickle for tensors, although Pickle has some problems. So we can't override all the behavior we would like to in Pickle. So pickling tensors is fairly inefficient, and also it doesn't preserve sharing storage. So if you do this and then do y equals, say, like take the first 2 rows. So these tensors actually share storage. Like if you mutate y by adding 1 to it, and you print x, you will see that the first 2 rows of x actually have changed. So if you now were to pickle, like a pair of XY, if you then loaded them, it wouldn't actually alias the same storage. So pickle has some problems, so you can use it if you really want. But our recommended solution is we have two functions for this purpose. So we have torch save and torch load, which are very similar to pickle, except that they're way more efficient because they have a lot more C paths than pickle has, and don't have to go through Python with all the memory, and they also preserve all the sharing correctly. So if I do XY, and you just give it a file name, so we can just save it as foo, and now we can load. All right, now we'll replace them. So that's X. Now let's add 1 to Y, and we can check that X has changed. So this preserves everything. So basically, these are the two functions that you should use in pretty much all of your code if you want to actually dump something to disk. All right. So that's the basic tensor level operations. It's very similar to NumPy, which probably most of you are familiar with. It's just slightly different conventions. So do you have any questions about this? All right, so now we'll move on to actually using Autocrat. So that's the probably most interesting part of PyTorch. So to use Autocrat, you have to wrap everything you have in variables. So you'll probably see this line a lot in PyTorch scripts. So as Sumit said, variable is basically a wrapper around tensor that holds the tensor, of course, holds the computation history that has created the tensor, and also holds the gradient with respect to this tensor, because it's often convenient to have them close. So we have this tensor x. Now we can make a variable by just wrapping x like this. So you'll see that the string form is very similar, except for the variable containing header. So variables are slightly different than tensors. There's only actually one type, because it's basically a box, but the one variable type can hold a tensor of any type. But operations on variable level actually dispatch internally to tensor level, of course, so you still can't mix and match types too much. All right, so now we can, or let's make it x, it would be more convenient. So now that we have x as a variable, we can do, say, y equals, we can compute where's the star? So we can compute polynomials, say of x. This is just a pointwise operation. All Python operators are supported. So this gives us a new variable y, which is slightly different than x, because if you look into its gradfn attribute, so you probably don't want to mess around too much with this because it's slightly internal. But if you look into gradfn, you actually see that so the last operation that was executed in here was this +1. So you'll see that this sort of points to the last operation that has created y. And if you look at x, it will actually have, so that's not printed in a Python, it's basically none. And so user-created variables never have gradfun, because they're not, we don't know how they were created. So this is what you can use to sort of check if they're user-created. And variables that have a non-grad function, we call them leaf variables. And so they're pretty important because by default, that's what most use cases need, and that's way more efficient than just storing all the intermediate gradients when we're computing. Only leaf variables get their gradients saved. So if you were to take y and now compute z as some other operation of y, we will never store the gradient with respect to y by default. There are ways to tell us that you want this grad, but I'll be covering this later. So now we have z, and we actually want to compute the derivatives. There are two ways to do that. Sumit briefly mentioned one of them. So there is this backward call. But one important thing is that, oh yeah, okay. So actually there are two important things. One important thing is that it won't work if your variable is not a scalar. So Autocrat only supports differentiation of scalar functions because that's basically what's needed to like run machine learning optimization. You only have a single output of your loss function that you're minimizing. Alternatively, you can look at it as a sort of vector Jacobian product, although that's, I don't know, I can probably explain that later if someone's interested in this. That's more, yeah. So the problem in here is that variables have two flags. There is a requires grad flag and there is volatile flag. So let's leave volatile for now because I'll cover that later. So the problem here is that I didn't mark the variable as requires grad. So by default, no variables require grad, like except for sort of if you create neural network modules, we know that they have learnable parameters. So we mark them as requires grad equals true for you. So this flag is sort of a way to make Autocrat more efficient by telling it like, you know, you're giving an image to your neural network, but you actually won't be optimizing the image and you don't care about the gradient of the loss with respect to the image. So we don't even have to compute that. So,
actually, I was wondering, if you want to freeze the weights of a network, you just put false to the...
Yeah. So the question was, what do you do if you freeze the weights of the network? So the way to efficiently freeze the weights of the network is basically the weights you don't care about, you set requires grad to false, and as much as we can, we just avoid computing gradients in that part of the graph. All right, but so if you wrap the variable like this, by default you don't require grad because users mostly create variables like this if they want to wrap inputs to their network. So that's the default choice. So to change this, you actually have to say requires grad equals true. Oh yeah, I changed x to be a variable now. So I'll just sample a new tensor, and I'll make it an x. All right. So now you can see that we have a new tensor. You can, of course, inspect requires grad status of these variables. So you can see that it was a problem. So the error was raised because z doesn't require grad. So these flags have sort of inference rules. So if you add two inputs that don't require grad, you basically get an output that doesn't require grad because nothing sort of in the history required grad so far. If any of the inputs requires grad, then the output will start requiring grad and it will sort of automatically propagate through the network. So in here it was a problem. We have only one leaf and it didn't require grad, so the output obviously didn't require grad as well. Now if we re-execute this cell, we'll see that this changes because like the only input to the only leaf, because leaves are basically input to sort of your computation, the only required grad, so the whole graph requires grad. So now we can actually run backward, but now we see the second problem, which is that you can only implicitly differentiate scalar functions. So for debugging, there is a nice hack. Like you just add sum, which basically computes a sum of all elements. This is very useful. Like if you have some problems in the middle of your model, and like you don't know what the shapes are, and you don't have to use your loss function to actually call to like compute a scalar out of something and call backward. You just sum all the elements and start backward from there, and like this lets you debug where the problems are. So now this was fine. We differentiate a scalar function, and this call actually has side effects. So if you look at x grad, it now contains a gradient of sum of all elements of z with respect to each element of x. So now you can like start optimizing this function and, I don't know, start looking for zeros of your polynomial. But that's probably not extremely interesting. All right, there is also, also it's sometimes useful to actually, in some cases you actually want to run backward like this. Say, if you have multiple, like, you don't want to sum the tensor for some reason, or you just have this output, or like you get the sort of gradient, you sort of have some implicitly defined loss function, and like the end of your graph is this implicit loss function, and you somehow magically get gradients with respect to all the outputs. You can actually sort of resume the differentiation from this point. You just have to provide it as an argument to backward. So this was a 5x5 element tensor, so in here you need to specify sort of gradient of the implicit loss function with respect to these elements as the argument. And all right. Okay, yeah, okay. That's another problem. So by default, we also try to be very efficient. So by default, once you once you differentiate a graph, we'll just basically step by step be dropping all the buffers we have, because this lets us save a lot of memory. Like if you just were to store everything, you would like need to store all the buffers for forward, and then you would also need to like incrementally build up gradients, which use up more memory in backward. We try not to do this, so by default, as we go through the backward graph, we sort of start freeing memory of the like later nodes that we already processed. So this kind of lets us, this pretty much lets us fit into the memory you needed for forward to compute the backward as well, for the most part. Like we still have to store some final outputs in like xgrad. So the problem is that by default you can't actually differentiate the same graph multiple times because we dropped these buffers. So now Z sort of only has a pointer to like an empty graph, so we actually have to recompute everything, and only now we can differentiate the thing again. And now we'll see that the grad has doubled because like the loss function of sum actually like emits all one tensor as the gradient of Z. So there is a way to avoid this. Like if you for some reason need to backward through the graph multiple times, now I need to recompute it again. But you can actually add an argument called retain graph true, and now you can do it as many times as you want. Although it's probably the best to like drop this argument for the last backward call to make it slightly more efficient. So that's one API. There is also another one which lets you, like, some people like to write in more functional style. So there is a function called torch autograd grad. So in a lot of other frameworks, you probably have seen like grad functions that sort of return new symbolic descriptions of the graph. In PyTorch, we do everything eagerly, so this actually also computes. So this actually like runs the computation. So if you run now you could just say that you want a grad of Z with respect to X, or if we had multiple, we can even, we can even take outputs with respect to multiple things, including variables that are internal to the graph. So that's sort of one way to actually access the gradients of the intermediates. And this call will return a tuple of gradients with respect to these things. So, all right, what now? Oh yeah, okay. So now we have this problem that Z is not a scalar. So we add our hack for sum. Everything worked. So this call doesn't modify xgrad now. This is purely functional because we specified that we want an x here. So the grad itself is actually an xgrad, and we can see that also we captured ygrad. Yeah, so these are two prime. Also for backward, if you have multiple variables that are say in multiple GPUs, we also have this torch Autocrat backward form. So you can actually say that you want to start backward from X and from Y at the same time. So they sort of share some parts of the graph downstream. This is more efficient than calling X backward and then Y backward. In general, in machine learning, it's a good idea to batch things, especially if you run on GPU. So this is definitely the recommended way to do that. Also, another important thing. So this functional API I showed before is especially useful if you want to do higher order optimization. So we can again compute, we need to recompute that. So you can again compute the grad of X. Right, and if you say create graph, which is a different flag, the previous one was retain graph. Create graph basically means that you actually also care about the graph, about the derivative computation. So by default, we also don't record the graph for this, just to be more efficient. But if you actually care about this, you can also do that. And now x underscore grad will have a grad fun. Yeah, that was correct. We'll have a grad fun itself. So now you can also now compute some expression on the gradients. Like in some machine learning models, it's fairly common to compute gradient penalty. So you compute your loss, you compute your gradients, you then take the norm of the gradients, you add that to the loss, and you this is your final loss. So this is the way to do that. You compute your loss in here, you add all your parameters in here, you get grad of all your parameters in here, you compute the norms, you add them together, and you go backward from this. And this gives you the final gradient of the function that you want to be optimizing. So the one last thing is a volatile flag. So pretty much everything I covered right now is for inference, is for training. But sometimes you want to evaluate your model on a test set. And for this, you don't care about creating any graphs and saving any memory for the differentiation. So if you mark a variable as volatile, it implicitly doesn't require grad, and it has volatile true, and volatile sort of propagates requires grad in the graph, except that it takes precedence over requires grad. So if you say you have your convolutional network, you're training it on ImageNet, and then you finish an epoch, you want to run evaluation. So then you don't have to reset all the weights to requires grad false and do all that. You basically just mark the input as volatile, and as the input will be processed inside the network, the volatile will take precedence, and this basically means that you can't differentiate the graph now, because this is just so that you don't have to modify your code to sort of efficiently run inference on models that are implemented using Autocrat, because mixing Autocrat and tensor level operations doesn't work. So far, we will probably, so what I was saying right now, the variable thing, at some point in the future, probably in the upcoming months, we'll be changing the API slightly so that the variable will be merged with tensor. Basically because we pushed the overhead of Autocrat to be very close to actual tensor level operations, so it doesn't really hurt a lot. And we're also working on optimizing inference in Autocrat, so this pretty much matches the tensor level overhead already, as far as I remember. So there's no reason to, when you'll see some of the actual examples that Luca will be presenting later, you'll see that variable calls are sprinkled all over the place. So we just thought that once you want to actually start differentiating things, you just say requires grad equals true, and like everything propagates automatically, and you don't need to think if like your function now has variables as inputs or if it has tensors as inputs. Also, variable API is exactly the same as tensors, so for most cases this should work. So one last thing about Autocrat. So I mentioned that we have a lot of in-place operations, and PyTorch users love in-place. So this is something that's not really supported in a lot of other frameworks. So if you have, let's make it requires grad. If you have a variable and like you compute some expression of it, right, now you can actually do things like, now you like sort of got information from somewhere, like from some environment, that you want to like zero the first row of y. So you can do this, and this works, and you can see that it's actually 0. So variables can be modified in place. This is not very common for automatic differentiation systems, and this like computes the derivative correctly. So in this case, if you were to sum this and backward from now, you would see that like x grad, like because the output didn't depend on the like original values in the x in here, the gradient is basically 0. So you can do this in Autocrat, although we kind of discourage this. You'll see this in one of the examples I'll be pulling up in a moment. There are some pitfalls, like if we change this, so add is kind of a special operation because it doesn't need to save any of the variables in here. If we change this to multiply, or yeah, I'll just make it x times x. So multiply actually needs x to compute the derivative. Yeah, sorry, the example has to go differently. So it will be like this. Now we'll say z equals y times y, and now we like in-place operations, so we modify y, and so we run some other parts of the models, and now if we backward from z, oh yeah, that should have been like that. So now if we backward from z, we'll actually see that this is an error. So we sometimes need to, as I mentioned, we sometimes need to save variables for backward. So in-place operations are slightly dangerous because if they were saved, we will still detect this. So like everything you compute is correct. The worst case scenario, you'll just get errors. The problem is that we can't really detect them early. So using too many in-place operations, if you really don't have to, can sort of cause some pain later in debugging, because this just tells you that, you know, hey, I was computing something, but and I saved something, but you actually modified it. So now you have to sort of go over all your code and try to find the place and figure out which in-place operation was this. And in-place operations don't really buy you this much, so I would recommend to be very careful with them and not really use them unless you have a good argument for that. Any questions for this part? All right. So that's sort of the next level. Now we'll move to NN. So NN is like the library for describing neural networks or machine learning models in general. So it's sort of the NN is also documented on our website. So if you go to the docs, you can like go to torch NN, and here you have like a list of all kinds of layers that we have built in and loss functions. So like, you know, we have dropout, we have convolution, and of course everything this. So that's the level of abstraction at which NN works. So usually in scripts people just import it as an N, so they don't have to write it like this, tart an N all the time. So we can, or like let's take the linear layer. So you just basically create the layers normally. So for example, linear layer takes in 2 arguments. like it requires two arguments, which is like the dimensionality of the input data and the dimensionality of the output data. So now if we create this, it will give us, like, it will pretty print that it's a linear layer that sort of projects 5-dimensional data to 10-dimensional data. Right, and now, so a few important points. NN only works with batches, so you never give it like 1D things. We pretty much only work with 2D and up. If you have, like, if you don't really do batching, you just have like a leading dimension of size 1, and that's like mandatory. So for linear, we actually want to have 2 dimensions. So there is the batch dimension. I'll just make it, say we have 4 examples in a batch, and then a feature dimension. So we said that there's going to be 5, so we're going to make it 5. So now that we have this variable, to use modules, you just use the call operator like this. They behave like regular functions. So you can do that. It gives you output. It again has like batch size of 4, and it now has 10 features and has been projected. Also, like, the input was, every example was constant, so the output is not very interesting. Now we can save the output, and so linear is a layer that has learnable parameters. Here you'll see that even though we created an input that doesn't require grad, we sort of like the computation of y involved learnable parameters. So now y will requires grad, and you can differentiate that. All right. So that's like an introduction to modules. Now, of course, using modules like this is not very interesting, so you often want to compose them into more complicated things. So we only have one container in an N because it's like very common. Like, you often just have sequential parts in your network. So there is an N sequential that basically you give it in the constructor. You just like say that now I want this linear, then I want sigmoid, then I want another linear, and sort of that will be some kind of a network. And now you can run this. So this will just like be passing the input to the first thing, output of this thing to the next layer, and so on. So this basically lets you save some code for writing like long compositions of modules. So LuaTorch used to have some more complicated containers, but we decided to not re-implement this simply because we think that it's much better and much clearer for the users if they actually implement this in their code. So for most models, you'll actually find people implementing a lot of custom modules. So to implement a custom module, use subclass and module. So of course you can write an initializer. So like we'll say that we want to know how many input features we have. We want to know how many output features we have, say. And now, so an important part is that you need to call the superconstructor. And now you do like self linear 1 is like an linear num inputs, and say it's going to be num output divided by 2. Then you do self linear 2. Or like we'll make it okay, so we'll sort of make it like this. So let's say we want to have a network that will compute, like, it will compute linear 1, it will then apply some nonlinear function to that, Or all right, let's like add 2 more. That will actually showcase some things better. All right, so we sort of have like 2 similar towers. So now we'll do like x in the path A will be linear 1a of x. Now x of a will be like in the feature dimension. Oh yeah. And also, so now we often want to apply nonlinearities. So it's sort of annoying to write them out in this form, except for NN sequential. So for things that don't really involve having learned, so if we have a functional API for an N as well. So modules are very convenient if they're things that actually have parameters, because they will like, you just tell them how many features you want and they will size the weights appropriately for you. Like you don't have to worry about this at all. They also like make sort of device like parameter management easier, as we'll see soon. But for things that don't have parameters like NN sigmoid, we don't really recommend using them as modules. So there is a functional package. People usually import it as F uppercase, just because it's used very often. So in here, you can just do f.softmax, not softmax, let's do sigmoid. So yeah, so functional operations, just use this. It's usually clearer than using modules, and you don't have to write you don't have to initialize the modules in the constructor, so it sort of helps. So now we like compute xb. Now let's say we want to apply tang to that for some reason. Now we want to like compute like a sum of this. So this is like a module with non-trivial dependencies. Like it's no longer linear. It's basically like have 2 independent towers that use different nonlinearities. Then you sort of merge them, and now you can like expand it again with those 2 linears going out and like return say 2 outputs that are 2 different embeddings. So now you can do return self-linear to A on x2 and self-linear to B on x2. Yeah. So, and also modules can have multiple inputs. They can have multiple outputs. All is allowed. Like they can pretty much take unstructured inputs and outputs, as long as you don't use hooks, which we'll cover later. This really doesn't matter. And you're free to like return dicts or even custom classes. Like people write modules that like recursively traverse trees and compose them, and that's pretty common. So there are no risks.
Sorry, can you make it bigger, because they wrote me that
it's all right.
Small. So
Feel free to speak up also if something's too small or unclear. So is that okay?
Thanks. Yeah.
I can probably make it even slightly larger. All right. Yeah, so that's how we write modules. So as Sumit has shown, what? Oh, it's probably not the height that's the problem. No, you can't. Oh, like, nope. No, it doesn't work with function. What's the shortcut? Is it control?
It should be in the view. Also,
All right.
there's like in the view here, header bar, toggle header, toggle bar.
All right. Okay. All right. So.
Sorry. In capital F, where is the file?
Okay. So capital F is just I just imported a module and aliased it like this. It's a fairly long name. Even functional is fairly long, so it's very common to prefix it to alias it with an uppercase F. Yeah. So I of course forgot to take in like. Okay. So now we have a net, we can actually print it. why didn't it print the modules? That's a very good idea. Okay, so when you have okay, so as I mentioned before, NN modules simplify parameter management. So, for example, there is a function called parameters. So this is a lazy generator. So if we actually want to get the list, I don't know why these are not registered. I must have made an error somewhere. Okay, I guess we go into live debugging session. Alright, maybe I'll just stop doing this. I don't want to debug this live. So we'll sort of jump into Torch Vision. So that's a package Sumit mentioned. Torch Vision has a models package. So for example, we can get ResNet 18. Unless we say we want it pre-trained, it actually comes with random weights. So we can create it like this. Now we can, so if I didn't have a bug that I don't see immediately there, this would sort of look like this. So networks, they sort of just iterate over modules that are defined inside, and they just print them like in a hierarchical way. So you can see that like in ResNet you have net sort. So these are attribute names, so you can actually like index them by this way. Sequentials, you just use the like regular list indexing to get them. So you do net.conv1, and this will actually give you the first thing that we saw there. Maybe I'll leave that up. I'll scroll down, or say like this is a more, so modules can also be nested. So in the way I assigned them in here, they should get automatically picked up and registered. So, and they can also be nested. So like we can do net layer 4, then we know it's a sequential, so we want to access the first module, and then like we want conv1, and this gives us exactly this module from our network. So as I said, in the constructor, you can actually, like when you assign modules to attributes, they are getting registered by NN. So if you assign a module directly, it's getting registered as a submodule like in here. So in ResNet constructor, someone just did self-conv1 equal NN conv2d with all these parameters, then self-bn1 equals batch norm, etc. Also, you can register raw parameters. So if you actually wanted to like create a module with some parameters yourself, because we don't provide it for you, then you can like do self.weight equals nn.parameter. So an n parameter it looks like a regular module, except that it's really like it acts exactly as a variable. It is a subclass of variable. So you just give it a tensor. And this thing, it's like, since it's a parameter, it implies you want to learn it. This actually by default will require grad. And if you assign NN parameter objects to weights, to attributes, they will also be automatically picked up as parameters of your model. All right, and also the third thing you can have inside your modules are buffers. So, maybe I'll just cover like moving things between devices. So there is this parameters helper. So conv2d, if you look at like source of conv2d, it just this self.weight assignment to sort of register its parameters, and then there is this generator that will like, it's printing, that mostly takes time. So parameters are prefixed with parameter containing, and so this will just basically recursively traverse the whole like tree of modules and accumulate them in this list. So it actually printed all of them. So these are like some biases of batch norm and like convolutional weights. There's a lot of them, so like I won't be scrolling through this. So it's basically a single flat list, which is very convenient when you want to give it to the to an optimizer, say. So we can see that ResNet 18 that I created has exactly 62 like learnable parameter tensors. If we wanted to like count parameters, we can do so there is a nummel function which like returns the number of elements in a tensor or in variable, because parameters are like variables. So we can actually also just do this, and this will give us the total number of learnable parameters in ResNet 18. Also, there is a way like to there are functions called named modules, so we can like do we can do this to sort of preview what it gives us, or like let's make it a list and like take the 5th element. So this will basically like iterate over all submodules recursively and return them with these names. So there are like a few helpers to sort of let you traverse these things. You'll see them also in Luca's presentation. And probably the most important feature of modules is that they let you sort of move all the parameters to the same device. So right now, if you like look up net conv1 weight, or you'll see that it's a torch float tensor, but like say we don't actually want to run the model on GPU on CPU, we actually want to run it on GPU. So we don't have to go over all of the parameters. It's enough to just call Cuda on the module. So this will take some time, and so this is slightly different than like calling Cuda on a tensor. So calling Cuda on a tensor actually returns a new tensor. Since cloning like complete trees of modules would be fairly expensive, calling Cuda on a network actually replaces all parameters in place. So now if we go to net conv1 weight and like print just the type because we don't care about the content. So, all right, so this is a variable. So, oh yeah, I forgot to mention, you can actually recover the tensor that's inside a variable, but by accessing its data attribute. So now we see that like the type of the conv weight turned to torch Cuda tensor. Also, we like say you want to move it to CPU back again, you just run this, and like all the weights, no matter which one you look up, they all automatically turn into tensors of appropriate type. Or like you can do net double if you for some reason experience numerical instabilities. That's fine. You just casted your network to like use double precision. But now you have to remember to give it double precision input, of course. All right, and the last thing are buffers. So buffers are sort of like tensors you want to keep around. There's some constants. So there is one example that I had in here. Yeah, I'll just copy this somewhere. I hope matplotlib works in here.
It should.
Okay, that's good. So, for example, some people write code that like they want to include sort of Gaussian blur as part of their networks, like to, I don't know, somehow spread the features. That of course can be made differentiable in PyTorch. So basically all the code in here, it's like we just this is also an example of like integration with NumPy packages. So we just import NumPy, we import SciPy filters, and now so these lines basically prepare a Gaussian filter. So if I just run this, if I look into raw filter, so it's like, you know, a or I can do. Does that work? Nope. Oh, because it's a, all right, I have to do to NumPy. All right. Okay, so we see that it's sort of like having decreasing weights as we approach the like boundary of the filter, and then so we would like to convolve this filter over like over our image. So we have to construct. So there is like a convolutional operation in PyTorch already. So we have to construct a weights for it only. Like we will use this filter as sort of the weights of the convolution, and they won't be learnable. Like, or you can just pre-initialize. But in this example, they won't be learnable. So convolutional weights have a format of like number of output channels, number of input channels. So we'll only be like working with like RGB input, RGB images, so we can visualize them. So it'll be 3 by 3 in here, and since the filter is 5 by 5, these are like filter sizes, so we'll specify it like this. So also convolution does like cross correlation between channels, and here we just want to like for the sake of this example, we'll be just blaring like the channel with itself only. So we just like sort of fill the diagonal weights so that each channel like doesn't interact with any other channels and is only blurred like based on itself. So now you could do, hopefully I won't make any errors now. Yeah, so now to sort of have this nice property of having, so this Gaussian filter will be something that we kind of want to keep at the same type as like the network weights, because like it will be, if the network is in Cuda, we'll be blaring Cuda images. If it's on CPU, we want to keep it on CPU. So for this, there is a register buffer helper. This is not as nice. Like there is also add module and add parameter helpers, but sort of people tend to never use them because assignment is just much simpler. So register buffer, we actually don't want to register all tensors you assigned because you sometimes just want to assign tensors. So you actually have to like specify them explicitly. So if you do this, of course, you have to initialize, and then like in forward. So forward function is something that actually defines the runtime of your module. You never use this function directly, just don't do that. You just use call operator. Call operator does some bookkeeping that's necessary, and then calls your forward function. So in here we'll use the functional interface again. So this will be like 2D convolution on the input. So this requires us to specify a variable, but we'll be keeping Gaussian filter, so it's just a tensor. So we'll be keeping it as a, so the first argument is a name. So it will be available under self-did Gaussian. So you just do this, and that's like the definition of your model. Now we can do, so this is also like, in here right now we don't have any learnable parameters, but it's also a use case for modules just to keep some sort of state that will be shifted around. So now we can actually allocate an image. Actually, let me make sure that the types match. What's the type of this thing? Okay, it's a float tensor, great. Okay, so we'll just allocate an image. So we only have a single image in the batch. It will have 3 channels for RGB, and say we want to make it 200 by 200. And we won't be optimizing it, and here we'll just like want to showcase the runtime of this. So I don't specify it requires grad. Now I can do blur on X. This will actually compute some variable. Now we can visualize this. All right, so X will be just some kind of, yeah, that's a problem. I shouldn't have given it the, I don't know why it doesn't raise an error. So I gave it a variable. The problem is that matplotlib doesn't really like variables, so we have to pause the kernel. All right, I'll just run all the cells. All right, we'll just run from here. Okay, we have X now. So now, oh yeah, I actually have a helper function. So another problem with imshow is that Torch actually uses a different layout for images than NumPy. So, and like all the Python ecosystem, because it's more efficient to implement a lot of operations in this way. So the default sort of for the whole ecosystem is to have like height, width, and then 3 channels. For PyTorch, it's different. For PyTorch, it's like batch, channels, height, width. So we sort of have to permute some dimensions to match this. So show is like a helper function that takes the data of a variable. It like for the sake of this example, we assume we only have a single element in the batch. So squeeze is a function that like removes a 0th dimension if it has size 0. Then permute basically means that we like take a permutation of the dimensions, so we'll have height, width, channels. Contiguous is just for performance, probably not necessary. And then we convert that to NumPy, and we give that to matplotlib. So if we do that with X, we see it's like random noise. If we do blur with on X, we can see that it's, it gets smoother and smoother. If we do blur of blur of blur of X, you see that it sort of, gets a lot smoother once we apply this multiple times. So now the nice property is that, all this happens on the CPU, but say now if blur was like part of the model and here it's just the only part. So if we do blur.cuda, now we can just do blur.Gaussian, and we can see that it was automatically like shipped to Cuda. So now if we were to run our network on Cuda, this would just work exactly in the same way, and like we would be getting exactly the same results. So that's it for buffers, I think. And also that's probably, oh yeah, last 2 important things about modules. So you saw the syntax with assigning them. You'll probably be tempted to like use lists of modules and like have a for loop over a list of modules because it makes a lot of things simpler. So also we're like not in the business of traversing arbitrary data structures when you assign them to attributes, because that would slow everything down a lot. So for this purpose, if you actually want to keep a list of modules or parameters, just say, like self.modules equals and then module list, and then like you do linear. It's sort of similar to sequential, except you can never, except that, or like, I don't know, nm conf to the whatever. So it's similar to sequential, except you can't run this. The only thing you can do, it sort of behaves like a regular list. So you just can do for module and self modules and all this. So if you were to just assign this list without this decoration, these modules wouldn't get picked up, just like these one didn't for some reason. But once you add module list, they're all like properly added, and they're all like moving between CUDA and CPU once you call this. There is also an unparameter list for parameters. All right. So that's probably these are like all the important parts about NN modules.
If I have a classification problem, I would like to use ResNet,
Mm-hmm.
but my image size are different, my classes are different. Okay, I have to retrain just the reconnected layer, for example. How can I modify the loaded network in order to train the network?
So the problem, yeah, so the problem with most of the models in Torch Vision is that, okay, so the question was that suppose we want to use ResNet, but our data sizes are different than the standard ImageNet, which is like 224 by 224. And what to do then if we just want to like reuse the pre-trained weights? So I don't think there is like an easy answer. I don't think there is like, I can't think of any way. Like you can probably just, so ResNet has like two parts of the network, right? So it has first one, which is like purely convolutional, and this one actually doesn't depend on the input size up to some like restriction that it can't be smaller than something because it's like decreasing in size, so you can't end up with 0. And then you have like a fully connected linear part, which is like size dependent, so you could probably take the first part and like train the other part, but I don't think there is an easy answer for that. Yeah, so if you have like ResNet, you can just, if you have like a network, you can sort of do another patch, like a patch of another network, like you can just do, and then you can do like net conv1, net bn1, net value, net max pool, etc. Like you can actually also take modules from another network and like use this to sort of patch your network in a different way, and yeah. So networks are not, modules are not tied to their parent containers in any way. Theoretically, you can also reuse like the same, like you can have the same module assigned as children of multiple modules, although I probably wouldn't recommend that. Like it works and it's supported, but usually I found that it like ends up making the code much worse sometimes. Sometimes it's helpful. Right.
Maybe we can take a break.
Yeah, I think it's a good idea right now.
Thanks, Adam. Break is over there. So there's coffee and wow.
So let's start again. Hello.
Hello. Thanks.
All right, so we'll just quickly finish with like 2 important things I forgot about, and then we'll move on to like actually looking into examples of code that uses PyTorch to run various models. So one very important feature, if you're going to be serializing modules, you can of course do this with torch save and torch load. The problem is that it internally actually uses pickle, so, and since like the whole model structure is defined by the model code, it will kind of like pickle when it serializes things, it actually like saves relative like module paths. So it will be kind of tied to your project structure, so if you rearrange things, it will break. So the recommended way of serializing modules we have is, okay, net is still a ResNet. So there is something called state dict. Yeah, it will print all the tensors. Basically, it returns an ordered dict with like keys being like conv1 weight, because you can actually do like net conv1 weight and get the tensor. So this is the thing that you should be serializing because it's sort of independent of your model structure. And like you can actually like, so the way pre-trained models are implemented, we just trained them. We like got the state dicts, we uploaded the state dicts, then you actually download the state dicts, and then you have net load state dict. So if you reconstruct a model from the code, like you can move the class around, you can import it from a different place, you can get a script from your friend, whatever, you just like create the class in whatever way you want, and then you call load state dict, and this will be basically like restore all the state of the model to like the format that your friend or you just like saved the checkpoint. Another important part, of course, is that PyTorch, like you probably heard that, you know, all the dynamic graph stuff and all this. So in PyTorch, Autocrat, of course, can handle arbitrary Python code. Like you can use coroutines, you can use generators, you can use whatever you want. You can do things like while x norm is smaller than 1000, then you like multiply x by 2 and like run the, okay. Yeah, okay, so x.norm, x.data, because like conditionals can be really on variables, we have to unpack the tensors and like drop to the tensor level, and then we like get an x. And this x also has a grad function, and you can just call backward on this, and it will correctly like compute the derivatives. It will basically count how many times this loop ran, and like record all the operations and differentiate that. Also, like one last example that's probably worth mentioning, it's kind of representative of integrating with other packages that you might find useful, and also with higher order gradients. So now it's like how this basically shows how to implement how to integrate, say, in here, SciPy functions so that they're compatible with Autocrat. So you import Torch, you of course import Autocrat, you import SciPy. So to extend Autocrat, you create a new class which subclasses function, and it needs two static methods. So one of them is forward, and then backward. So forward is what actually computes the function, backward is what computes the derivative of the function. So you get a context object that is, so the same thing will be given to forward and backward. If you need something in the backward, you actually need to save it in the forward. We don't have a lot of time, so I won't be like going very in depth into this example, so we can move on fairly quickly. But like basically on our website you can find docs that like explain line by line what happens in these in this code. So you just like get a tensor in here, you run the SciPy function on this, you cast it again back to Torch tensor, and you return that. So this is this is the density of like a normal distribution. So I won't be going into like the derivative. It's like you basically need to, you know, sit down with SymPy or with a piece of paper and do this. Then you get this norm PDF class. You can take its apply method and like assign this to a function, and this like looks like a regular Python function. You can use it on variables as you want, and it will call the SciPy thing, and actually so if we run this, what's the problem now? I forgot some casts somewhere. Where is it? It's in here. Okay, so it should, oh yeah, because the problem is that it's, I've been using a master version of PyTorch. So in master version of PyTorch, in some places you actually can now even ignore casts to NumPy, because we've made tensors implicitly, like you can just give tensors to NumPy functions and get back tensors, and it works. But on this box that I'm running the code on, this actually like that's just the like package version, so it doesn't have latest commit. So in here we then use this function, like we like take 1,000 points distributed equally between -5 and 5. We compute the density. Then we like just do the sum and get the grad. Then we take the second order derivative of that, like we again sum the grad and get this, and then we just plot 3 lines like xy, xx grad. So it's the first derivative of the PDF, and it's the second derivative of the PDF, and then just show this. And so you basically end up with like first derivative, second derivative. No, sorry, that's the function, that's the first derivative, and that's the second derivative. So integrating with like arbitrary Python libraries is also fairly simple, and like that's probably what was used to implement this primal dual optimization in that blog post. I think we don't have a lot of time, so we'll probably end this like dense part of going into going over all the APIs, and we'll actually move on to the examples now. So are there any remaining questions? All right, then I'll just leave it to Luca to introduce some examples.